Licia Verde, con Statistical Techniques for Data Analysis and Cosmology.
Okay, so last of the 3 lectures on statistical techniques for data analysis and cosmology. Here's the idea of what I want to discuss today. So last time I promised I would say something about going beyond parameter fitting, but I didn't have time, so I will start with that. And then I'm going to introduce a powerful technique for forecasting. Not the weather, but how well an experiment can do. And this is called the Fisher matrix approach. And then I use the Fisher matrix approach to give a little introduction to model selection, because in the Fisher approximation, then there are a lot of things that you can do analytically that otherwise you just have to write down the equation and say, you know, go and compute this messy integral yourself. And conclusions. So before we start, from the discussion I had with some of you and some of the questions in the discussion session, I think it's important to say a few words about statistical versus systematic errors. And there's a little devil there, not just because of the drink that is called Licia Verde, but because the problem, systematic error are a problem. Now, statistics and probability theories and everything we can talk in a formalized course can tell you how to deal with the statistical error. There are always systematic errors. And the important thing to keep in mind is that as your data set grows, and that's we have experienced this in cosmology in the past 10 years, the statistical errors shrink, and they shrink rapidly, but the systematic errors do not shrink. Well, you can build a better experiment that has got less systematics, but still. So when this error becomes smaller than this error, you have a problem. Now, unfortunately, there is not a recipe that fits all to deal with systematic errors. But Rumsfeld can help. So Rumsfeld taught us that there are known knowns, that there are known unknowns, and there are unknown unknowns. So this is also how we can characterize the systematic errors. There are some systematic errors we know, and we know how to model them. And those are the easier ones to deal with. There are systematic errors that you know you have, but you don't really know quite well how they behave. And then there are systematic errors that you don't even know you have and don't even know what they are. Alright, so this, of course, the unknown unknown, the things that you don't know, are the most difficult one to deal with. There is a lot of interesting literature in the past, say, couple of years that started popping up on how to deal with the known knowns and known unknowns. And basically the idea is, you parameterize your systematics, you use those as extra parameters and then you marginalize over those. And in the case of known unknowns, there are examples where you actually try to expand them in basis set and then do techniques like path integrals and things like that to actually also marginalize over those. And then in the past couple of years, also something else has popped up. And I popped up simultaneously, not just in cosmology, but also in particle physics or dark matter searches and things like that. That is, if you have different observables that you know are affected by the same systematic effect, but in different ways, you can find a way of combining the observables so that the systematic effect cancels out. Right? A typical example for cosmology is the example of actually trying to measure the growth factor. right, of perturbations. And so you know that you have the problem of biasing. When you measure the beta parameter is directly related to the growth factor, but you have a B in there. But B comes at the bottom. And then you have another quantity that is called sigma 8, that when you measure it, it usually can multiply with something like B. And so if you now say, well, my two observable, I combine them by multiplying them, this bias should sort of cancel out, at least to first order. And this is one cosmological example of what I mean, and it's cropping up in several different forms, several different fields. The other thing you want to keep in mind is knowing when to stop, which, you know, in my case, it was sort of difficult to learn. So you can try to improve your modeling or improve your control of systematic errors. But the name of the game is that you basically want the systematic error to be below the statistical errors, and that's it. So there's no point to shrink the statistical error much below the systematic errors because you hit an error floor there. And there is no point to actually lose entire night of sleep to make systematic errors factors of 100 below the statistical error because this is time waste. And so it's also important to know when to stop. And I'm not going to say anything more about this because there's no recipe, and so that's what I can tell you. Okay, so let me give you an example because it came up in the discussion. And this example, I always put it under the name, how do you know you are not fitting the noise? So imagine you have some bunch of data, and so you have this data, and you have a y, which is a f of x, from some noise. Can you learn f from this data? Right? So, and this is an example of a powerful technique that is called cross-validation, which is very useful to know when you are detecting or not the noise. So you have something like this, so let's consider the method. You can try to fit with a linear, you can try to fit with a quadratic, or you can try to fit with join the dots. Okay, so why not choose this one? Which obviously this is going to give you a much better chi-square than this or this. Right? And how do you know which one to choose? And so the idea is, what do you really want? You want to know how well you are going to predict future data that are drawn from the same distribution. And then obviously, if you're using this is not very predictive. And so you don't know the next one whether you're going to put it there or there. While in the other case, this is very predictive because you're going to get an extra data point, you know exactly this is going to go like this, and you know exactly this is going to go like that. And so there's a balance there. And so I think we want this one. And so the idea is to use the training test set approach, which in the limit it could be called leave one out cross-validation. But I'm going to explain all in the same slide because it's exactly the same concept. So you want to split your data in a training set and a test set. You train in a subset of data. So you randomly choose X% of the data to be your test set, and the remainder is the training set, and this test set could be all minus one, right? And that becomes a leave one out cross-validation, but you have all possible choices in the middle. The remainder is your training set, perform your regression, imagine you want a linear regression sample, and then estimate your future performance with the test set. So you define a cross-validation score, which is usually the distance between the test set and your function. And this may remind you of training set for photosys because it's basically exactly the same thing. And so in this case, and this is an example from actually an online textbook exactly in statistic, and this is a particular example where they do leave one out cross-validation, but it works exactly the same. So in this case, you have a CV score that is like that. As you increase your degrees of freedom of your curve, these are, you know, two parameters. This has, you know, just a line. This is curve. This CV score improves, but then the join the dot increases again. And so in this case, you say, well, you choose this because you minimize your CD score. Okay. So you have a balance between predictability of the model and fitting well the data. And now there's a whole long discussion of which way is the best to split your sample, whether to do in leave one out cross validation. That's in principle the ideal one because you don't waste much data each time you throw away only one data set. But it is extremely, extremely expensive, so there are very, very long discussions about which technique is the best, and the one you need to choose depends on your particular problem and your computational limitations. Okay? And so let's say something else about beyond parameter fitting. So one thing is to go non-parametric, and now there's, I believe, nothing that is really purely non-parametric. And so the way of saying is going minimally. And so, for example, a working example could be the shape of the primordial power spectrum, which is an interesting example for cosmology because it's related to the mechanisms that set out the initial conditions. And so when you do parameter fitting, you usually use forms like power laws. And if you're adventurous, you may want to put the running of the spectral index. And you may put it in here. But other popular options are, instead of feeding a function to the data, you may want to use a basis function. And there are examples in the literature of using wavelets, principal components, etc., etc. And this is an example, again, taken from one of the WMAP papers, of actually just binning your K and just reconstruct the P of K in bins. Of course, again, this is not fully non-parametric because the number of parameters is the number of bins you have, but it leaves much more freedom to your fitting function than actually fit into a power law. Another example that you can find in the literature are piecewise linear, you can find Chebyshev, you can find splines, and the sky is the limit. Okay. The other things that you can do, you can try to say, well, I have different models with which to fit the data, and how do I choose between the different models, right? And so in the example that we had before, in here you have two parameters. You add the running of the spectral index, you have 3, but here you have as many parameters as the number of bins. This is going to improve, of course, the chi-square compared to a fit like that. But maybe you don't need 15 parameters to fit something that in reality is really a straight line. And so, in cosmology, we started discussing these things, well, from around 2003, 2004, and then the discussion has exploded since then. So let me show you some example of things that are being used. One is called the archaic information criterion, that says, well, take the log of the maximum likelihood. Well, this is, you will recognize it that if everything is Gaussian as the chi-square, that's the chi-square. And then you say, well, but you penalize it by something that goes like the numbers of parameters. So the more parameters you have, you need to really improve the fit a lot to offset the fact that you added parameters. There is another criterion that is similar to this, as you see, but it doesn't just weight or penalizes by the number of parameters, but also by the number of data points. Because it makes sense, right? If I have 15 data points and 15 parameters, I can of course fit everything. But the most sophisticated approach, and the one that actually people have tried to show that in some limit goes into this and goes into that, so the much more general one, is what is called Bayesian evidence. So what Bayesian evidence does, it does not focus on the best fitting parameters of the model, which is what this does, right? But rather ask, of all the parameter values that you thought were viable before you actually look at the data, how well on average do they fit the data? And not just as the best fit. Okay? And so mathematically, this is little like that. You are integrating over all the parameters, your likelihood, multiplied by the prior. Okay? And so this is saying, of all the parameter value that you thought were viable before you actually look at the data, right? How well on average they end up fitting the data. Now, this is very cool and probably actually answer the question you are asking more directly, but it's really computationally expensive. So there are packages to help you. And these packages are publicly available, you can download them, install them, and run them. But know that doing this sort of integral, this is a highly multidimensional integral, it's not a joke, and that's where the Carlos technique really helps you, because doing this problem exactly in high-dimensional space is impossible. Okay. So let's try to understand more or less where this comes from in the concept of in the framework of Bayes' theorem. So when I brought Bayes' theorem, I brought it this way, and I say, well, let's keep it general. Let's put this an hypothesis, and this hypothesis could be a model, or could be within a model the choice of parameters that I choose for this model. But in reality, when you go and do model testing, you've done parameter fitting already, and so you may want to be specific of exactly how you're using this theorem. So for parameter fitting, what you're actually saying, you're always putting the hypothesis here, and you want the probability of the parameter, not of the hypothesis, right? And so when you want to find the Bayes factor for the model itself, then what you can do, as I was saying before, you're basically trying to normalize this expression. And so you're trying to compute this denominator, which is again, as we said before, the integral over all the parameters of how well on average does your model fit the data. And so this also comes back to one of the questions that I was asked, right? When you do the chi-square, you know exactly how to normalize it. When you start by Bayesian, you lost the normalization. And so when you're doing chi-square, you have the very big advantage that you can do reduce chi-square, and then you can look at the minimum chi-square value, and you know exactly what the probability distribution of that minimum is, and you can find the goodness of fit. While when you go Bayesian, since up to now we always forgot about the denominator, we say, well, you got the data, so forget about the denominator. Then we lose that extra information, that goodness of fit. And in this way, you are basically recovering it. But the price you pay is that these integrals are painful to do. Okay, so there's not much more I can tell you at this stage about this. And so I'm going to move on, and I'm going to introduce the Fisher matrix approach. Now, probably many of you have already dealt with this. How many of you have used the Fisher matrix approach? Yeah. So, but since some of you have not, then let me go through it anyway. So, let me give you some cosmological example of kind of question you may want to ask in cosmology. So, for example, you can do hypothesis testing. So, say, are cosmic background data consistent with the hypothesis of Gauss initial fluctuation? Are CME plus larger scale structure data consistent with the hypothesis of a spatially flat universe? There are questions you may want to ask, like parameter estimation. What is the value of the matter density parameter in a standard lambda CDM model? What's the value of the other parameters today? And these are the most straightforward questions to answer. And the Fisher matrix approach is very powerful in these kind of problems. But then we try to stretch it and go down to these kind of questions. That is more like model selection. Is there evidence for a non-flat universe? Is there evidence for a non-constant cosmological constant or dark energy? So before we go on, we need to go back to likelihoods a little bit and just write down things in a mathematical way. Now, unfortunately, I keep switching between theta parameters and alpha parameters of my models because theta is not used for other things in cosmology, so depending on what you are doing, and alpha also. But so I will always say parameters when I use either theta or alpha, so you don't get lost. So in here, define X to be your data vector. And this may remind you of the random variables we defined at the very beginning in the first lecture. And this could be the temperature value of pixels in the CNV map, Fourier coefficients of density of galaxy in a survey, and things like that. And then we define a vector of model parameters. Okay? And the likelihood of the data given the parameters is the probability distribution of your data. Since your X is a random variable, also your parameters will be a random variable. That's why you can compute probability distribution for those. So ideally, the name of the game, you want to find an estimator, a way to compute the average values of these theta parameters that are the two underlying model. So something written like that, it means that the estimator is unbiased. If here I had to write plus epsilon, then the estimator would be biased. And we've heard about biased estimators before, but now I don't remember who's see, yes, related to length. And then the other thing that you want to do, you want to minimize the error of the estimator. You minimize its variance. And so you want the best unbiased estimator, makes sense. So that's where the Fisher informator matrix comes in. That's from Fisher, 1935. And so what it says I define this curly L as minus log likelihood, and then I define a matrix which is the second derivative of this curly L with respect to the parameters, and I take the average value of that. And you can, the maximum likelihood estimator for your parameters is the one that maximizes this L. And then if you do that, there are a number of powerful theorems that apply, and you can look it up in Kendall Stewart. This is a series of statistical books, but what we are going to do here, we are not going to prove any theorem, we are just going to use that. And so it says that for any unbiased estimator, the errors on your parameters cannot be better than what you can derive once you've computed this quantity, which is the Fisher information matrix. Okay? It can only be worse. And so the error on the parameter I is always greater or equal than this f to the minus 1 element I to the 1/2. Okay? Or in case this is diagonal, then this is what it becomes. This is called the Kramer-Rao inequality. Okay? This is very important to keep in mind because it's also a way to test whether there's something weird going on with the analysis of your data. If you do your data analysis and you end up with very, 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 very nice error bars, but these error bars are smaller than what you would have predicted a priori by doing this calculation, which now I'm going to show you why it's that powerful, because you can use it without even having done your survey, then you know that something is wrong. And there are illustrative examples of this. All right. If there is a best unbiased estimator, it is the maximum likelihood estimator or a function thereof. And the maximum likelihood estimator is asymptotically the best unbiased estimator. So, maximum likelihood estimator is what you really want to use if you can. So, the cool thing of the Fisher matrix approach is that it's a quick and easy way, although not always accurate, to tell you how well a future experiment can do without even you looking at the data, without even you building the instrument that actually will allow you to collect the data. So that's really powerful. And so we've seen what the Fisher information matrix is, but basically, what are we want to do in here? So remember, this is roughly, right, 1/2 data minus theory, covariance matrix inverse data minus theory. The theory depends on the parameters. And then you can say, well, since I want the average value, I can say that this is 1/2 fiducial minus theory, c to the minus 1/2 half fiducial minus theory. And now, once you go data to fiducial, now you don't need the data. So to develop intuition in one parameter case, and for a Gaussian likelihood, what you end up having is this expression, and what is the second derivative of this expression? Basically, this is a curve. You are taking the curvature of this around the maximum. So in general, you're basically expanding in Taylor series around the maximum, and because the first derivative is 0 by construction, because you sit yourself in the maximum. And so this is what you have, and which reminds you of the chi-square. So all it is a quadratic expansion around the maximum. And so this quantity here is nothing but the 1 sigma displacement of your parameter from the maximum. It's like a measure of the width of the peak, which is all what errors are. So let me back up a second about this, again, because I recall some of the questions. So in principle, right, when you have some data and you do an experiment, have some data, analyze the data by fitting that to a model, all the information is included into your form of the likelihood, or if you're Bayesian, into the full posterior, okay? But usually when you publish a paper, you don't have space to actually publish in the entire posterior or the entire likelihood. So what you want to do, you want to compress this information in one or two numbers. And so what you do, you just compress all this into an error bar. Okay? Now, if you now go and give your colleague that error bar, your colleague has no way to find out what the full distribution was, unless the distribution is Gaussian. Because if it's Gaussian, you know I only have to give you the variance and you know everything. So if in a paper you see something with asymmetric error bars and you want to do your statistical analysis on those data, you have a problem, because if they are asymmetric error bars, obviously the distribution where they came from was non-Gaussian. You don't know what it is. And so you have no way of actually using them properly unless you go and contact the author and say, give me your full posterior or your full chi-square. Okay? All right. So in the multi-dimensional space, we are restating the Kramer-Rao inequality. So the variance of the covariance between parameter I and parameter j is always greater or equal than the inverse of the Fisher matrix elements ij, and only if all other parameters are fixed, then you can say that the error on parameter alpha I is greater or equal than 1 over square root of 1 over the element fii of the Fisher matrix, only if all other parameters are fixed. While something like this gives you what you call marginalized error. That is the error of one parameter marginalized over all the other one. Remember, you have to perform a matrix inversion here. And if you have many parameters, it's a big matrix like that. Okay. So let me repeat this. There is a fundamental difference between conditional and marginal errors. Okay. So the conditional error is this one. It's the minimum error that you can have on this parameter if all the other parameters are known. This error is almost never used. What you usually want is the marginal distribution of your parameters that is integrating over all other parameters. And again, since things are Gaussian and we know how to deal with them, it turns out that you have to do this matrix inversion first, and then take the element ii of that matrix. And usually this error is bigger than this one, unless the matrix is diagonal. There's no covariance between the parameters, right? So what are we saying really? What we are saying is that the probability of the data, given your model and your set of parameters, can be written like this. So remember, this is parameters, this is your Fisher matrix, and these are parameters. But remember, I can also tell you that this is the likelihood, and then this is is equivalent to say data minus model, covariance of the data, data minus model. So this is sometimes called Laplace approximation. But again, we assume everything is Gaussian, we only keep the variance and we have written this as a Gaussian. So we make the Gaussian approximation. But I think this is really cool because here you need to know the covariance for your data, while here you have the covariance of your parameters. The left-hand side is the same, but you need to know completely different things here and there. Okay. The cool thing is that, as I will show you, you can compute this without having your data, while this you need to know your data. So let's make a little bit more explicit calculation. So let's assume Gaussianity and drop the relevant constant, then 2 log likelihood is log that of covariance plus data minus the theory, covariance minus 1, data minus theory. Where this is the data covariance, and the data covariance can depend on the parameter. Think about the cosmological background and think about cosmic variance. That's the underlying parameter. So you can show that the Fisher matrix, and therefore the covariance for the parameter can be written in terms of that for the data. And it will take this form, which sounds really complicated, but we can learn a couple of things from this equation. So this is matrix inversion, and this is taking the matrix and taking the derivative with respect to parameter alpha and the derivative to parameter beta. And this, in this n alpha beta, this is defined as derivative of the data vector, right, done this way. The cool thing is that here you need the data, but here all the data dropped out. This is your theoretical model. So you don't need the data. You can know how well some data set can do without even going and building the experiment to actually collect those data. And so this nicely simplifies in some specific cases. It simplifies depending on whether the dependence on the parameter is in your data or the dependence on the parameter is in your covariance. And you can always find several different examples of that. Okay? So keep in mind that this is the full expression, even though in many papers you find that several different terms are being dropped, and sometimes some assumptions that are not always justified are being done in dropping some terms, so keep always this in the back of your mind. Okay, the other options that you have, if you don't want to go through this pain, is simply to compute this explicitly, taking the data to be identical to a fiducial model. But in this case, you need a numerical second derivative, and doing numerical derivative is always a little bit of a mess, so always test the stabilities of your derivatives before proceedings. While in this case, you only take one first derivative, so it's numerically much more stable and easier to compute. So again, you can compute the Fisher matrix before you do the experiment, and then therefore you can use it as a tool to design or optimize the experiment. However, you made a big assumption. You have linearized everything, you have assumed Gaussianity, and you are only exploring things around the peak, around the fiducial model, and if that's not correct, then maybe some dependence of your error bar on the choice of the fiducial model. But within the assumption made, now you have everything, and you know everything. Now the sky is the limit. So say you have worked with 5 parameters models, but now you want to keep parameter 1 and 3 fixed as a fiducial model, because you work with a model that is a lambda CDN, plus running, plus is non-flat. You've done all your derivatives, but now you say, actually, I didn't want to have it running and non-flat. I want to have it power low and especially flat. Then you can do it. You just have to do matrix operations. So Now you put 5 parameters, but now you want to keep parameter 1 and 3 fixed at the expedition model. So you take the sub-matrix 1, 3 of Fij. Suppose, say you have 5 parameter Fisher and you want to plot the joint to be forecasted constraint for 2 parameters, for parameters 2 and 4, marginalize over the other parameters, then invert Fij, take that sub-matrix 2 and 4, invert this back, call it Q, and Q now describe your Gaussian 2D likelihood, and you can look up your delta in the famous delta chi-square table, then you can also draw ellipses. And when you look at the forecasting paper and they plot all these nice ellipses, that's what my experiment will do, they went through an exercise like this. They probably do the calculation in many parameters, and then they reduce the parameter space in this way because plotting. What happens if you want to reparameterize? So let's distinguish a couple of things when we talk about reparameterize. There's one way you can decide to reparameterize, that is change the type of parameters you're dealing with, omega mater or omega mater h squared. So it's very good before you start doing Fisher calculation to know that your likelihood is as close as possible to Gaussian, because you've done the Gaussian approximation here. So if you start with something that is close to Gaussian, then you're not going to make a big mistake. And remember, things may be highly non-Gaussian in a set of parameters, but then you can reparameterize and make it look much more Gaussian in the other set of parameters. Remember, for the cosmology background, using h and omega cold, or using omega cold h square and theta, the theta parameter. So before you start embarking into Fisher calculation, you want to do something like this to get something much closer to reality. But say you are dealing with two different data sets. Say you are dealing typically with cosmic microwave background and baryonic acoustic oscillation. So the set of parameters that make the cosmic microwave background likelihood as close as possible to Gaussian are not the same set of parameters with which you want to work when you do forecast for BAO. So for example, in the cosmic microwave background, we already know which parameters we want to use. They are the typical parameters being used by, for example, Cosmology. But for BAO constraints, the BAO parameters really are the Hubble parameter as a function of redshift and the angular size distance as a function of redshift. And if I really want to be fully precise, this should actually come in combination with the sound horizon and radiation drag. This is not always mentioned because current and future experiment will give you such a small error bars in this quantity, at least for the standard cosmology, that error bar is much smaller than this one and you can forget about it. Okay. So what do? Well, since we are in the philosophy of Fisher, where we are doing small, we are moving very little from the maximum and just measuring the curvature around the maximum, we are reducing everything to matrix operation. Then since we are doing very small changes in the parameter, we can linearize the relation between one set of parameters and the other set of parameters. And then basically what we are doing to the matrix is we are doing rotation and stretching. So the idea, the expression is the following. You have some old set of parameters called theta, and then some new set of parameters called phi, and you simply do a change of coordinates, which for matrices is done this way. And you are done. So to summarize, this is what you do. So your total Fisher matrix for your BAO survey plus the CB plus the other survey, you take that, you invert it. If you want to marginalize over nuisance parameters, with nuisance could be systematics that are being parameterized, or could be parameters that are there that you're not interested on. So you invert, take your submatrix, invert it back, and then if you want to combine with the cosmic microwave background, then you have some BAO basis you need to project into your new space. Now you have the Fisher parameters for your new parameters, and then if you want the covariance matrix of the error of your parameter, then you're doing inverting back. This may sound a little bit complicated, but at the end of the day, this is just matrix operation. usually linear algebra, which we study at undergrad, and you can know how well something can do without rebuilding the experiment, which takes a longer time and with much bigger effort. Now, if you don't want to code all this up, there are practical tools out there, and one very useful one is called iCosmo. These are some examples of plots that are produced by the package iCosmo. So I recommend iCosmo because the source code is fully available. You just can download it and start using and start modifying. It's written in IDL. It's interfaced with CAMP. And you can also have a web interface. So if you don't want to actually install it and run it, you can do very quick tests directly from the web interface. And a tutorial course on iCosmo happened in my group, and the notes from the tutorial and the exercise and everything, you can find it from a link in there. So if one day you need to download this iCosmo, start using it, and you have questions, probably a lot of the questions are answered in the link to iCosmo from them. So let me go back a second to systematic errors. Can the Fisher approach account for systematic errors? From what I told you so far, it looks like no. We just deal with statistical errors. So in general, no. But there's an exception. And let me try to walk you through this. Imagine you have two competing models. And this is also going to be an introduction to model testing, all doing the same steps. Model n and model n prime. N has n parameters and n prime has n prime parameter, and n prime is less than n. So we are saying also that the two models are nested. So n prime is a particular case of n, where you fix one parameter. So if the two underlying model is n, and you instead fit the data with n prime, which is smaller, which have less parameters, the maximum expected likelihood will not be at the correct value for the parameters. And so, if n minus n prime is equal to p, the n prime parameter will shift from their value to compensate from the fact that the p parameters are kept at the wrong value, because we're using the wrong model. And so, if the t parameters differ by delta psi from the true value, the other parameters are shifted by an amount that within the Fisher approach you can compute. And so, this is an example of a systematic error. It's a systematic in a theory, right? But this is an example of systematic error. And so, this may sound complicated, but this is just the Fisher matrix for the model with prime. This is the shift in the parameters, in the psi parameter. This is the shift in the theta parameter, and this is just a subset of the original Fisher matrix. So once you have the Fisher matrix, you have everything. Also to compute something like that, you need the Fisher matrix of the big model, of course, not of the small model. So visually, this is what's going on, okay? So if you have these two parameters, so this is the larger model that has got an extra one, and the true value is here, and these are the likelihood contours. But now imagine that you say, well, in the smaller model, I forget about this parameter, I just fix it at this value. Say it's the curvature, I say this is the curvature, and this is zero curvature. And imagine that the true model is there. Then, of course, when you do your fit, you're going to find that the best fit is here. So this other parameter has shifted to compensate for the fact that you have the wrong model. And so this is very useful. An example of this has been used to find the effect, for example, of neglected is a curvature contribution, or neglected effect that can delay recombination, or effects due to, say, neutrino masses or neutrino properties that go beyond the standard model. And there is more. So in the next 5 minutes, let me walk you through the evidence, because in the Fisher approach, in this Laplace approximation, you can also compute the evidence relatively easily without doing messy integral because a lot of things simplify. So remember the evidence that you have to do this messy integral? So let's go back to the models MM and M prime. So I can write now the ratio of the probability of the model M prime given X, the probability of the model M given X inside the posterior. And then, since I'm taking the ratio, then the other bit drops out, and I'm left with this. And this bit here with the integrals, which looks a lot like the evidence, no surprise. This is the bias factor. It's called B, the bias factor. So, how do we proceed from here? For non-committal priors, we can just say that my prior of M is equal to prior of M prime, so this is unity, and then this the base factor is just these two integrals. Well, it's the ratio of the two evidences. And now, instead of having one messy integral, I have two, but let's go on. So what are we saying here when we look about the base factor? M will have higher likelihood, or at least as high as the model with less parameters. But the evidence will favor the simpler model if the fit is nearly as good because it's got a smaller prior volume. So you are saying you are basically penalizing models with more parameters unless they fit much, much, much better than the one with less parameters. So for uniform and separable priors, these simplify to something like this. And if the prior is wide enough to encompass the sport of the likelihood, that is where the likelihood is significantly non-zero, which is something you should always do and have, otherwise you get nonsense, then this bit also obviously simplifies. Now, this again still requires a painful multidimensional integration, but in the Laplace approximation and approach, and Fisher can come to the rescue. And so we recognize that in the Fisher frameworks, we can write the things in terms of determinant of Fisher matrices and ratios of the likelihood at the best fit values. And you now already know how to compute all these terms, and you will see that this simply simplify in something like that you basically know how to compute. Once you compute the Fisher matrix, you have everything. But of course, you have to do the Gaussian approximation. So let me leave you with an example. For example, if I say it's gravity described in general relativity, that's my question. And then I have data set to say Euclid plus Planck. And so I'm going to use the famous gamma parameter that Eric knows very well, and basically parameterize the growth, the linear growth of perturbation. And then you can plot for a survey like that what this Fisher approach to base factor will tell you. And then you can see you have inconclusive, substantial, strata of destiny, to decide the evidence, and GP is here, and GR is 0.55, so 0.55 will be. So you can do curves like that. So in the last few minutes, let me go to this. So some people ask me, can you give me some example on how to compute the likelihood for specific problems? Because we've already done an example with Gaussians. And so let me go back to likelihood and work you through an example. So again, it's an example taken from the Cosmology background. So the Cosmology background temperature fluctuation distribution is close to Gaussian, and so the angular power spectrum, the CLs, are not. And at low L, the central limit theorem, which is something you always invoke so that you can use Gaussian and do all this very nice thing and simplification, it does not hold. Because for every L, you have very few N. And so what you need to do, you just need to do what is said in the Khan. Right? Do what said in the label. So your likelihood for the temperature data given the CL is a Gaussian, but for the temperature fluctuations. And so, and the signal covariance, it's written like that. These are the Legendre polynomial, and these are your CLs. So this is a typical example where the dependence on the parameter is actually the covariance. Okay? So once you've written something like this, you can now write in spherical harmonics. If something is Gaussian in real space, spherical harmonic transform is also Gaussian. And then isotropy means that you can sum over the ends, and you end up, the ALN become data, and CL theory remains CL theory, and you end up with an expression like this, where CL data are related to your ALN. So now that's your likelihood. You can show, and I give you as an exercise to show that with noise, CL theory goes in CL plus noise, and with partial sky coverage, as long as your patch of the sky is large enough, then you can do simply approximation of putting an F sky in front. I leave that to you as an exercise. Okay? The CMB light, however, is polarized. There is not just the temperature, and you can easily generalize the above, and you end up with an expression like that. So this is all good if you want to do Fisher forecast, but when you are actually given a real map, things are more complicated, and you may need to do things that are much messier than that. And this is again taken from one of the WMAP paper, and I'm not going to go into the details. First, because it's math and you have to just sit down and work through it yourself, and second, because my time is almost up and I don't have time. But I walked you through some approximations that are used and that are really powerful and also useful for you as an example of how to deal with this problem. So remember, we end up writing an expression like that, at least for the temperature, and we're not going to use the more complicated one also with the polarization. Other approximation that were used in the literature before were the Gaussian approximation, where you will recognize this as the inverse of your covariance. And the log normal approximation, which is written to look like this, but where operation has been done to this Q and to these CLs, so that this is a log normal. But what you can do, you can take this expression and expand it around the maximum. So just say my CL data is CL theory, 1 plus epsilon, epsilon is small, and then I expand. And you end up with an expression like that, and you stare at it for a while, and you say, oh look, this is 1/3 of a Gaussian plus 2/3 of something that is extremely close to this, but with a change, so these are not the data anymore, these are the theory CLs. This works extremely well. This turned out that this approximation works extremely well at L greater than, say, 20 or so. Now for Fisher, I just give you a proof by intimidation that the likelihood that I wrote before, that messy one that had data and theory, if you want to get rid of the data and just be left with models, third can be simplified into something like that, where x and y define t, b, and various combination, and where this covariance is this. And this is a proof by intimidation because going one way is much easier than doing the proof the other way. Have fun. So, let me conclude. If tortured sufficiently, data will confess to almost anything. Please remember this, and so remember what I add to that. Treat your data with respect. So, I would like to thank the Scientific Organizing Committee and the local organizing committee and all the terrific work they've done to actually make sure that we really enjoy this week. I enjoy my stay here a lot so far, and thanks also to the whales that accompanied us yesterday. And I leave you here with a list of references. This is is all going to be on the web, so don't scribble all down. All right, thank you.
Are there any questions?
I have many questions, but I think we can discuss them later, which are more or less really technical. But one thing that I really find hard in Fisher is always calculating the derivatives and deciding the right step for the derivatives. I know that this is a very technical question, it's numerical, but I asked this question to many people and they couldn't really answer, so I try with you. Do you have, because for example, for Lambda-CDM parameters, the derivative of the power spectrum, you know more or less which should be the step of your derivative. But whenever you explore some new parameter, it's very hard to decide which is the right step for the derivative, to make the derivative. So do you have a criteria to choose that, or?
Okay, so the step you can use in computing your derivatives, it's limited on the numerical effect that you have when you actually end up taking differences, okay? And so you want to take a large step because then the differences between the two models is much bigger than the numerical effect. But if you take a large step, then maybe the Gaussian approximation completely breaks down, and then as you take steps of different sizes, there will be a dependence on the results on the step size. So there is no rule that tells you what step to take. I mean, in principle, if you had no numerical errors, what you have to do is a derivative, and the derivative, remember, it's as the step size tends to 0, but in practice we can't do it. So the rule of thumb is take a step that is comparable with the size of the error bars you're expecting that parameter. Because if your numerical errors are bigger than the size of the error bar you're expecting your parameters, there's no way you're going to get anything out of this anyway. Fisher or not Fisher.
Right, my point is that sometimes it's hard to
know it a priori.
know when you're touching your numerical
yes.
limit in some way. And sometimes you have like 100 parameters, and doing that by eye, it's very hard. So you should in some way...
So one way you can do it is, if you don't want to do it by eye, run it for several different step sizes and make sure that the answer does not depend on that. Otherwise, you just need to plot your derivatives or your function and make sure that your function behaves and you don't see numerical effect. Otherwise, you need to go into your CAM code or whatever that is and just make sure that the numerics are under control. There's no easy.
Yeah, I was hoping it's something.
Okay.
Okay.
You know, some people may say compute it on a grid and then interpolate on the grid and take the derivative of the interpolating function. Could be dangerous.
Are there any other questions, comments?
Could you back to the slides on the estimation of Fisher matrix, estimation of a systematic bias based on the Fisher matrix?
This
Yes. Yes. So I think this formula is relying on the fact that the theta is quite small because we expand the log derivative. Yeah. So, but we think this is important only when the theta is quite large, right? So how do you justify?
Okay. Yeah. If it's Gaussian, then it doesn't matter. And we made the approximation that everything is Gaussian. If it's non-Gaussian, or then all hell break loose, but that's an approximation you need to make. There's a price you pay doing this thing before you get the data. That is, you have to make an approximation. Yeah.
Is there a good question, please?
So, log by lambda, the inverting Fisher matrix means marginalizing errors, but I didn't have quite intuitive sense why inverting Fisher matrix gives marginalized error. Could you please give a short explanation about that?
I think you can see it in several different ways. I mean, probably the most transparent but heavier one is just write a Gaussian and just do the Gaussian integral. But at least Gaussian integrals, we know how to do them, right? So analytically, so. Sorry.
Thank you.
I think we have to move to the next speaker. This is the last lecture of Licia. So, on behalf of the Organizing Committee, I thank you.